Thanks for the introduction, and thanks to the CSCS for hosting this workshop and making it a reality. We are really happy for this first collaboration, and we hope we will have more. And thanks for your interest. This is our best reward. So as Marcel said, let me give you a little bit background on myself. I'm professor of statistics at the Università della Svizzera Italiana, and I co-direct the Interdisciplinary Institute of Data Science that started recently. I will tell you a little bit more about the institute as we go on. I will mostly focus on data science because that's my own expertise, maybe a little bit less on HPC, high performance computing, but this will be topics that will be discussed, of course, during the workshop. So let me start with a little story. Once upon a time, there were people like you and me, and then the big data wizard came and transformed us into bytes and stored us in a computer. And our relationships became ones and zeros. One if there is a friendship, for example, if you think of this as people, nodes, and links as friendship relationships. And those relationships were visualized as big networks with different colors highlighting the strength of the relationship when we go from zeros and ones adjacency matrix to a matrix of weights. For example, how many times I call a friend or how many likes I put on his or her web page. Well, in this image, you see a communication network in particular of 7 million nodes and 23 million ties. This is a data set that we have been dealing with, and I will tell you more about this data. So in order to understand and make some sense out of this data, to extract information and make this information valuable knowledge, the Interdisciplinary Institute of Data Science was created at USI in recognition of the fact that we are witnessing a revolution and we are living in a new era of data-driven scientific discovery. And the Institute is committed to addressing the demand that this data science brings forward, both from a research point of view and from an educational point of view. We are designing master's and PhD courses and in data science. These are the competencies areas that are already present at Università della Svizzera Italiana. Specifically, I work on predictive inference on a Bayesian, from a Bayesian point of view, and computational statistics, Monte Carlo and Markov chain Monte Carlo simulation. And I will tell you more about this. We have the IDIDS, directed by Jürgen Schmidhuber, the next speaker, who is an expert in machine learning and specifically in deep learning, long short-term memory. I guess he will tell you about that. And then we have colleagues that are expert in spatial statistics, econometrics, mathematical modeling and simulation. We have an institute at Università della Svizzera Italiana, which is called the Institute of Computational Science, ICS, whose director and other researchers specifically do mathematical models and simulations. Colleagues that are experts in social science and relational data, colleagues that know about privacy and policy issues and also ethical issues that big data arise, and many other areas of expertise that are already present at USI and that the Institute wants to network and enhance. Let me give you a feeling of the data science or big data related projects that require supercomputing or HPC. I'll give you some highlights without going deep into into them, specifically because some of them are really just starting. For example, Smart Lugano is a project that we are discussing with the municipalities. And of course, if we want to make a city smarter than what it is, we know that a city generates lots of data in very many different sources, health, mobilities, Internet of Things, and let alone retail and energy. And elaborating, storing, and making some sense out of this data, of course, require the help of the Swiss National Supercomputing Center and their supercomputers. Another project that will make our city not only smarter but also healthier is a project that we're bringing forward, or they were working on, with the Cardiocentre and the Fondazione Ticino Cuore. Lugano is a beautiful place to live, but there's more than that. It's a good place to have out-of-hospital cardiac arrest, because the time for an ambulance to reach you if such an unfortunate event happened, and the time to reach public access defibrillator or defibrillator in general is fairly short compared to other cities, and we are working on making it even shorter. Typically, having a defibrillator within 100 meters from the event is considered as the distance that would be enough to save your life, not only to save your life, but to make your life still worth, without having brain damages. And here you see a map of the current location of defibrillators, and on the left, and on the right, you see a zoom of this area with the defibrillators and the events of cardiac arrest that we have had. And you can see that maybe those two defibrillators would have been better placed around here, okay? Using optimization technique and merging different data sets, the one from the Fondazione Ticino Cuore that has data over the last 10 years over the Ticino region of all the call for emergency and the ambulance intervention, and with the data of buildings in the area, we are trying to optimally locate defibrillators in the area to shorten the time and save lives. Those are two case studies. We have many more. People here in this room have access to patent data, and we're trying to analyze this patent data, trying to understand how innovation spreads and knowledge moves around geographically and over time. We have people here that work on liquidity exchange data. There's a database of European banks that exchange money, typically overnight, but not only. We have people in this room that work on international trade. Other colleagues work on Wikipedia data. They also form a network with pages linking to other pages, and we're trying to make a sense of what makes a page a prime page, a page with lots of hits. We analyze data from social media to be able to do nowcasting. So people on social media talk about what happens to them in an instantaneous fashion and in a not mediated fashion. So they typically tell the truth. There's no need to say, look, I had to wait a long time to get into the hospital, or I had a long queue this morning going to school or to work. And this allows to perform nowcasting. And we also analyze social media to not only do sentiment and opinion mining, but also argumentation mining. So those are projects that we're working on with other colleagues at Università della Svizzera Italiana, but not only. We have a network of experts that we connect to throughout Europe and also elsewhere. So what is big data? Let me see if I can show you this video. Because I turned this off. About big data. Okay, this is a buzzword that we all have heard about.
Reconfigure and consult the data.
Of course, great idea. We have exclusive access to big data. Isn't that right, Mike?
Well, the truth is we have data, but not big data.
God damn it, Mike. I told the clients we had big data.
Well, when I said I had access to big data, I mean I know of big data. I'm just, I don't know him personally.
I know you're struggling. I can feel your pain. Your profits, they be falling. Encircling the like train. You're selling beer to babies, diapers to teens. You barely even know what your customer needs. Then stop. Oh yeah. I got a feeling the dude's about to aggregate. No sequel. More reduced. Maybe you should check what kind of data you're using and whether it illuminates.
Okay, I'm sure you'll be able to enjoy the video. But they mentioned Spark and they mentioned big data, so I thought it was fun to look at. So what is really big data? There are various definitions, inconveniently large, inconveniently because our data that we're not used to analyze, complex to handle, come in a breeze, the 4 V's, volume, velocity, variety, and variability. I'm pretty sure that you know all these type of definitions. Let me read you a quote by Terry Speed, 2014. Big data refers to things one can do at a large scale that cannot be done at a smaller one, to extract new insight or create new forms of value in ways that change markets, organizations, and the relationship between government, citizens, and more. Well, I don't really like the term big data, also because big data can be small, or what we mean by big data can be really small data. But typically they are complex, unstructured, distributed. I prefer the phrase deep data or smart data, and it is us that make the data smart. It's not the data itself that it's smart. There are terms like fat data, referring to data with small n, number of samples, and large p, number of variables. These are fat data, if you visualize as a matrix. We store them in banche dati, and this gives a value of the value that this big data contain. And indeed, the value chain extracts information from this big data, transforms it into knowledge, and knowledge should help us make a decision, often in real time, and lead to actions. So some data on big data. Here you have 2 graphs on Google Trend. If you search for big data and data science. So in red, we have over time how the search for the term data science has increased over time. And in blue, you have big data. Of course, those are 2 buzzwords. But you see that big data has sort of reached a plateau. Those down patterns that you see are 25th, 26th of December. On the other hand, data science is still increasing. Let me show you a couple of graphs of what is called the Gartner hype cycle that looks at terms that are becoming popular or that are popular and highlights 5 key phases in their cycle. So the initial phase in the time visibility axis is the technology or innovation trigger phase. Then we have a peak of inflated expectation. Then we go through a phase of disillusionment slope of enlightenment, and then plateau of productivity. So let's look at how the terms big data and data science or other technology-related or information-related or statistically related terms are positioning themselves or have been going through this slope. So here's the term big data in red highlighted, and how it moved along this curve from 2011 until 2013. So you see that it was in the emerging phase, climbing up the curve, and it reached the peak in 2013. If we go forward in time, 2014 and 2015, you see that the term big data is going into the disillusion phase, and the term data science here, it's rising up. And in 2015, the term big data is gone. We have still data science and machine learning. So big data is nowhere to be seen in the cycle in 2015. And as I said, in 2014 is already going through the disillusionment phase. And machine learning made its first appearance in this chart or these graphs in 2015. And a new term that is emerging is citizen data scientist that is appearing in 2015 and is expected to reach a plateau in 2 to 5 years and reach the innovation trigger region shortly. And what are these citizen data scientists? Well, they were defined by the director of this Gardner's research that produces these cycles as people on the business side that may have some data skills, possibly from a math or even social science degree, and putting those skills to work exploring and analyzing data. So why is statistics interesting and important in this data science era? Well, again, let me quote a colleague of mine, David Danson, who said, I would describe statistics as the science of variability, meaning that the main goal of statistics is to develop methods and algorithms for the mathematical exploration, elicitation, and control of variability, and the uncertainty that variability generates. Inference and uncertainty quantification are at the core of statistics, and they have created siblings like prediction, testing, controlling for dependence, confounding, and randomization. So without variability, there will be no statistics. And certainly in this big data, there's a lot of variability that we want to make sense of. And variability creates uncertainty, and statistics tries to do uncertainty quantification at all levels of this big data value chain. So there is a model-driven approach, and there is a data-driven approach. As a statistician, I favor the model-driven approach. I think we cannot make some sense out of data without a model. Big data also means big errors, or the famous phrase, there are lies, big lies and statistics. Well, with big data, the lies can be even bigger, especially if we do not have a model to support our prediction, testing, and conclusions. So this is a chain that highlights, again, the role of statistics in this data science era. So data are, of course, generated, and we generate data all the time. We use technology. Needs to be stored somewhere. If it's big, it can be stored on supercomputers. And then it needs to be manipulated. And as statisticians, we access the data after it went through a phase of cleaning. And there's actually some issue related to the fact that as statisticians, we don't see the raw data, but we see the data that went through some stages beforehand. And I will get back to this point later on. But so the statistical challenge is mostly at the bottom of this data science or big data value chain. So we model data and analyze them, trying to learn, and the knowledge that we extract has to be actionable knowledge. That is, has to be useful to support decisions. And then, of course, once decisions are made, they need to be implemented, evaluated, and then there's, this feeds back to the cycle. This generates further new data, and the cycle continues. So this is where statistics can really make a difference. So what are the challenges of statistics in this big data era? Well, I would identify three big challenges. Trying to make inference with multi-resolution data, multi-phase, and multi-source. I'm taking inspiration from a paper published by Professor Xiaoli Meng, the director of the School of Statistics at Harvard, and the paper was recently published in Statistical Science. So multi-resolution, well, taking an engineering term, part of statistics is try to separate the signal from the noise. But what is the signal and what is the noise is really changing. What was perceived as noise a few years ago is now becoming signal. And we dive to find signals in what would have been discarded as noise a decade ago. Multi-phase. This refers to the fact that when data arrives to my desk or to my disk, it's almost never the original data, the raw data, because the raw data is perceived as too dirty, too confidential, or too large to make it all the way to me as a statistician. So there is this pre-processing phase, and this pre-processing phase is done sometimes by more than one team. Somebody cleans it, somebody makes it so that it doesn't violate confidentiality issues. And this pre-processing made by different teams that have different goals make different assumptions. So when the data comes to me, it's too simplistic to use a single model to handle the heterogeneity that is being added to the data because of this multi-phase pre-processing. So we would need a multiplicity of models to capture the multiplicity of incompatible assumptions that are made in this pre-processing phase. And then finally, this multi-source. Data these days is not just numbers. Data are videos, images, GPS coordinates. There's a definition of data that is very diverse. So different sources of data, and many of these sources are not collected for inferential purposes. They exist just because it's cheap and convenient, and because we have big memory to store the data. And this creates additional problems when we analyze from a statistical perspective, because there's sampling bias, because this data is observational, it's self-reported, and as statisticians, we need to take these challenges into account when we analyze this data. Again, on the role of statistics, statistics help with data reduction, summarizing data, and data compression, which is relevant when we have big data. Helps in controlling the error rate and how it propagates into the inferential process, and helps in assuring coherence among different scale and different of time and space. For example, for the data that we have from the Ticino, Fondazione Ticino Cuore, Data is collected in time and space, and there was a lot of work done for pre-processing the data, and coherence is not always easy to ensure. And then, as already said, statistics should support real-time decision making, and I already told you about big data, big models, and big lies. Those are things we should worry about. So why Bayesian statistics, which is the approach to statistical inference that I value the most and that I typically use when I analyze data? Well, within this model-based revolution, the Bayesian methodology can allow for a few key features. First of all, we can think differently about the unknown parameters. So we can ask, what are the possible values of the parameters? In a Bayesian perspective, parameters are treated as random variables, and so are missing values treated as random variables. Everything that we do not know is treated as a random variable, and we can use some prior knowledge that we have on this random variable prior of seeing the data and incorporate this prior knowledge in the inferential process. So we can ask the question, what else do I know about this parameter and this model before seeing the data? And we can use the answer to this question in the inferential process, and will help us making better predictions. And moreover, the Bayesian approach allows to describe and take into account the uncertainty not only in the model, not only in the parameter, but also at model level. So again, we can answer questions about how sure am I about the inputs and the outputs of my model, and we can quantify the uncertainty about the model. We can do not only model selection, but also model averaging. If you have two models, two or more models that are competing, and then the Bayesian approach will allow you to say, well, a posteriori, in light of the data, this model has a posterior probability of being the good model, the model that has most likely generated the data, with a probability of, 50%, and then there's another model that has a probability of 40%, and the other remaining models have smaller probability. Well, are you really confident that you want to use the model that has the highest probability, 50%, to entrust for your prediction? Or maybe you should rather do model averaging and do your prediction based on those two most likely models that have generated the data. And then, moreover, the Bayesian approach allows to describe complex system and complex data using a hierarchical structure and multi-level models. So these are the pros of the Bayesian approach to statistical inference. Let me give you the big picture of statistical inference for those of you who are not statisticians. Well, typically we're given some data, big, small, deep, complex, and let's call the data Y, N is the sample size. And we come up with a statistical model that is typically indexed by a vector of parameters, say a d-dimensional vector of parameters. And we have some observed data, and if we are Bayesians, we can elicit some prior probability distribution on the value of the parameter theta before seeing the data. So given all of this, we want to come up with some probabilistic statement about the parameter, which is our unknown and that we treat as a random variable. So we want to answer a question like, which value of the parameter has most likely generated the observed data, and which interval contains the true value of the parameter with a certain level of probability, say 95%. Okay? Let me focus a little bit on the statistical model. Well, there are different types of statistical model. The ones that most of you are probably used to are models that are specified in terms of a family of probability distribution functions that are indexed by a parameter. For example, this is the Gaussian model, and we all know that the Gaussian model is indexed by two parameters, the mean and the variance. Sometimes the statistical model is much more complicated than a Gaussian model, and we all know that the world is nor Gaussian nor linear. So the model is specified up to a normalizing constant. That is, for example, if I were to give you the Gaussian likelihood up to this normalizing constant, I would tell you that the model is proportional to the model of the data, the product of these functions, and I'm omitting the normalizing constant. Well, if the model is very complicated, often the normalizing constant is not easy to write down, especially for those hierarchical or multi-level models. And the challenge is to make inference on the parameter even if the model is specified up to a normalizing constant. And Monte Carlo, and specifically Markov chain Monte Carlo simulation, allows you to do this. But then there is a third level of specifying a model, even with less information. Those are what are called simulator-based models, or generative model, or mechanistic models. They arise from physics, and they use the knowledge domain of where the data has been generated. And those models are not specified through an explicit likelihood function. So you don't have this expression, nor you have this expression. You can only have a mechanism that, given a set of the parameter values, for example, if I tell you what is the value of mu and sigma, given a set of parameter values, allows you to generate some pseudo data. So those are the models where we would really like to make the inferential process that statistics allows to do point estimation, confidence interval, hypothesis testing, model selection, and model averaging in a setting where you cannot write down the likelihood function. So in this setting, the probabilistic statement that we would like cannot be made, because you cannot maximize the likelihood, because you cannot write down the likelihood, not even up to a normalizing constant. But not only you cannot do maximum likelihood estimation the way we know it, you cannot do Bayesian inference the way we know it, because the Bayesian paradigm tells you that you should take the likelihood, multiply by the prior, and Bayes' theorem tells you that the posterior distribution of the parameter given the observed data is proportional to the likelihood times the prior. But if you cannot write the likelihood, you cannot access the posterior distribution of the parameter. So this type of classical inference, maximum likelihood and Bayesian inference, as you know it, is not available if the likelihood is specified up to a normalizing constant, and even worse, if the likelihood cannot be even written down for those simulator-based models. So how can we do likelihood-free inference? That is, inference, come up with probabilistic statement about the parameter in a setting where the likelihood is not available. Well, there are various existing methods, and I will not tell you much about what else is available. I want to focus on simulator-based models and the approximate Bayesian computation framework. So why simulator-based model? Because simulator-based model allows us to use the knowledge domain on how the data have been generated without having to make too many assumptions on the modeling phase. Those simulator-based models provide a nice interface with physical, social, medical, biological knowledge of the data. They scale well with data. They have no limits on the number of unobservable or latent variables, and it's easy to consider the effect of intervention on those type of mechanistic models much easier than it is in statistical models. So those are many good reasons that make us simulator-based model interesting. And there are very many examples where those models exist. Astrophysics, biology, weather prediction, ecology, health science, and so on and so forth. So in this type of model, you can use Markov chain Monte Carlo simulation But what I want to tell you about is, since time is running out, I want to tell you about the approximate Bayesian computation framework because Rito will expand on this. And this is a project that we are running with the CSCS. So I want to tell you a little bit more about this approximate Bayesian computation framework. It's a fairly recent and a new idea. The very first paper appeared in 2002 in Genetics. And then there are a lot of papers, mostly in bioinformatics, biometrica, and not very many into the typical journal that statistician reads. So what is at the base of this ABC, approximate Bayesian computation? Well, first of all, as I said, the likelihood is not available in closed form. You cannot evaluate the likelihood at any given point. You cannot write down the likelihood explicitly. That's one issue. The second issue is that you have big data. So how do we overcome this? Well, first of all, we summarize the big data through some summary statistics. We call the summary statistics S. So we go from the original likelihood, the distribution of, the original model distribution of y given theta, that as a likelihood would read that as how likely is the parameter theta in light of the observation. And we substitute y with a summary statistics. But then we have the problem that this function is unknown. So we approximate the likelihood using the fact that these models are simulation-based. That is, given a set of parameter value, I can generate pseudo data from the model. And once I've summarized the data with S and I've approximated the likelihood, we also have an approximate posterior distribution when we plug in into Bayesian formula this approximate summarized likelihood. So the ABC framework is an iterative procedure, and this is why we need a high-performance computer, because we need to simulate over and over these three steps. We first select a possible value of the parameter. Let's call it theta star. Given this value of the parameter, we use the property of the model, which is we can generate pseudodata given as input this value of the parameter theta star. So let's call the pseudodata y star. And we use the supercomputer to simulate this pseudodata given the model. This can be highly computationally intensive step. And then, given the pseudodata, we compare it with the observed data, the real data that we have collected in the real world. So we have simulated data, simulated on supercomputers, and real data collected outside in the real world. And we accept the value of the parameter if the pseudodata is sufficiently close to the observed data. So in order to make this working, this paradigm, this ABC framework working, we really need two things. A measure of discrepancy between the simulated data and the observed data, and a way of summarizing the data through some statistics. So let's go back to this image I showed you about. Suppose this is my big observed data. This is the mobile phone communication network of these many peoples and with many different ties and links. Actually, this is a snowball sample of this huge network. The actual data does not fit on a computer. Well, actually, it might fit on these computers, but not on my personal computer. Okay. So in this network, we have nodes that represent subjects, and in general, they can represent statistical unit of observation, and edges that represent interaction among the nodes. Think about friendship data or communication data, but there are many systems of scientific and societal interest that have a large number of interactive components. For example, the web page links, protein-protein interaction networks, citation networks, advisory networks. So let's think of one such mechanistic network, and let's make it an example that we can all understand. Think about a friendship network. So from the perspective of a subject I and the time this subject spends with friend, well, the subject I can spend time with existing friends, and let's say this happened with probability delta, so it reinforces a link with friends that already knows, or it can become friend of a friend, so I can spend time with this friend of a friend, and thus creating a new link, or it can make totally new friends, okay? So this is a mechanistic network model, so we use the knowledge domain of social sciences that tell us how we build friendship relationship, and it's a model that is governed by those two parameters, a delta and a W. So think about this model as a black box model, and this is our mechanistic model. So we have used knowledge domain to build this model. And now think about inputting in this black box possible values of this parameter, delta and W. And using the supercomputers, we get out some pseudo data. So for some setting of the parameters, we get this pseudo data. Other setting gives rise to different pseudo data. And then the ABC methodology aims at comparing the observed real data with the pseudo data. So which one of those pictures is closer to the observed data? So here we have the simulated data on our supercomputers, given different values of the parameter. On the left, we have the real data. So we ask ourselves the question, which ones of the Y star is closer to the observed data? Well, we have generated some value of the parameter, theta star, and if we are Bayesian, we generate these values from our prior distribution. We then simulate a data set, pseudo data, using the supercomputers, and then the value of the parameter is accepted if some distance between the observed data and the pseudo data is less than some threshold. This is the essence of the approximate Bayesian computation paradigm. And thanks to Rito, who is a postdoc at the Interdisciplinary Institute of Data Science, and we are working on a joint project with a colleague from Harvard School of Public Health, J.P. Onella. And thanks to the help of the CSCS friends, we are setting up on their machine a prototype framework to perform approximate Bayesian computation. And as I was telling you, the big data are summarized through summary statistics. We need a distance measure. We need some threshold epsilon that tells us how close we want the summary statistics on the observed data and on the pseudo data to be in order to accept the value of the parameter that has been generated. And if the statistics S is a sufficient summary statistics, we do not introduce an additional layer of error in our inferential procedure. But you know that if you do not have a likelihood, you cannot tell whether statistics is sufficient for a parameter. So what we use, again, is knowledge domain to come out with relevant summary statistics, relevant for the decision or the prediction purposes that we have in mind. Let me stop here and let me summarize. So I hope I've given you a feeling of what is big data, what is data science, how we at the Interdisciplinary Institute of Data Science are contributing to this data science revolution. Data science, I see it as a new paradigm to scientific discovery. What are the challenges that this big data pose, and how can HPC help in trying to make some sense out of this big data that we have, and specifically focusing on one methodology, this approximate Bayesian computation methodology that we are currently working on. And Rito will expand on this in the next few days. Thanks for your attention.
Okay, good. So let's start with let's say the official part of the workshop, where we do some hands-on stuff later and speak about some organizational things. And I also, so in this session, I also try to give you a kind of a big picture how data science fits into the things we are doing here at CSCS, into the high-performance computing part. But first, let's speak a bit about the agenda and some organizational stuff. So we have 3 days. So today, essentially, we are giving you an introduction to Spark, to the MapReduce world. We speak a bit about how you program MapReduce programs, how you access our systems. We will set up everything so that you can work with your notebooks. The workshop will be pretty much hands-on, so a lot of the time you will be working on your notebooks and trying to do exercises and reading stuff. And then the second day, we will focus a bit more on specific problem-specific aspects of data science. So we will have a look at machine learning. We will look how to apply the Spark machine learning library. We will have one session about Bayesian statistics, so the stuff Antonietta talked about before. And we will also have a look at how to do graph processing in Spark. And then the last day is a kind of a mini hackathon. So the idea is essentially that with the knowledge you gain so far, you can try to work on your problems. So you can, for example, try to parallelize things with Spark. You can join discussions with others. And we are around, and we try to help or to involve ourselves in discussions. But it's really quite open how we manage this last half day. Then before I start with a general introduction, one more comment. So during this machine room visit and the coffee break, there is another a meeting happening in this room. So for this time, we have to move out all our stuff, and we can put it somewhere in the room in the entrance hall. And then we have the machine room tour and have a coffee break, and hopefully by then the people are out and we can move again in. That's the only time we have to do it. For the rest of the days, our stuff can stay here. Good. I think that's it. So now let's have a general overview, get a bit the big picture, and afterwards, so at the end of the session, we try to get things running on your system. Okay, so what I want to convince you essentially in the next 30 minutes or so is that parallelism is very important, that you all need it, and that you can use Spark for it essentially. Okay, and why is this the case? Well, because there are big problems out there. So there are not only big problems in HPC, also in the data science world and data analytics, but let's first start with the HPC world, because this is an HPC center. So numerical intensive problems here usually look along these lines. You have the real world, you model the real world somehow, then you do simulations on the model in order to predict the world. Okay, and there are various examples now. I mean, there are molecular dynamics, there are finite element analysis, there are weather prediction. Let's just have a look at weather prediction. I have to get used to these keys. So, how is a weather prediction model looking like? I mean, this is a bit of hand waving. And what I essentially want to say is that it's a big problem. So what people do is they take the Earth, they decompose the surface of the Earth into squares, say 1 × 1 kilometer, and they slice the atmosphere in, let's say, 100 slices. And then for every little cube you have, you want to know 6 variables: temperature, humidity, pressure, and wind speed, which is 3 directions. So that is how a very simple model can look like. And then you end up already with pretty much cells, so 5 × 10 to the 10 cells. And then if you want to, I mean, this is the model now, and now you want to simulate and do predictions. And if you do very simple estimates, you suddenly see, okay, the required space for this model is already 2 × 10 to the 12 bytes, which is 2 terabytes or so. So this is already quite big, in particular if you have to keep the model in the main memory. And if you want to do a 24-hour forecast to know how's the weather going to be the next day, well, you can do a calculation on the time steps. Then you see, okay, we need 1.5 × 10 to the 17 operations. And if you assume that your computer can do 1 teraflop per second, then you see that the simulation itself takes already 1 day. And it's a little bit pointless to do this simulation, because when the simulation is done, your data is worthless and not predicting anything. So this problem is quite big, and it's somewhat challenging to solve this problem, and you need way more computation power than a teraflop per second. But now let's have a look at another problem from the data science perspective. I mean, a standard thing the big internet companies are doing, they are crawling the web and doing some analysis on the stuff. You as a researcher, you can do the same. There are public data sets for web crawls, for example, this one, a web crawl corpus. You can download it from Amazon, and it's 500 something terabytes. This is quite big. I mean, if you want to do analysis on it, you have to read it at least once, right? And if you say you have a standard connection of 1 gigabit per second, well, you need around 6 days to go through the data once. This is quite a lot, so also a big problem. And then, well, what can you do if you have such problems? Either you wait for, you buy more hardware, buy a faster computer, or you wait until the computers are fast enough. So there's this Moore's law that we heard previously, that computing power increases every 18 months or so. But in terms of a single CPU that becomes faster and faster, this trend now flats down, so it comes somehow to an end. So this is not really an option. The option would then be to parallelize. That means to use many CPUs, many computers to solve your problem. And the type of parallelism is not only limited to CPUs, but also to other aspects like memory or disk. So these 500 terabytes of data from the web crawl does not fit on a single disk. So you have to think about how can I store this in parallel, so to say, on several disks. Okay, and this is a bit about the development that is going on in recent years. I mean, this is a famous book by Tony Hay, and there the authors essentially claim that, well, this traditional way of looking at science, like having a hypothesis and testing it with an experiment, a simulation, so, well, does not come to an end, but maybe gets extended by another type of scientific process, which is called the data-driven approach, where you do not start with a hypothesis to look at your data, but you start with the data itself, and you look at it, and then you build up your hypotheses about the data. And this is becoming also more and more important, and if you look at the data that is generated every minute, you see that it becomes more and more simple to get large amounts of data, which in turn then are required to have, where you in turn are required to have a parallel infrastructure to store it, to analyze it, and so on. Okay, so meanwhile, I hope you are convinced that parallelism is good and that we really need it. Maybe you might meanwhile think it's the holy grail. So I have a big problem, I just throw parallelism at it and everything is good. That would be great, but it's clear that this is not the case. Also, parallelism has limitations. There are practical and theoretical limitations. And I just want to quickly give an overview about these limitations. So on the theoretical side, we have Amdahl's law, which essentially states that every problem might have an inherent sequential part that I can't essentially parallelize. And the bigger that part is, that the more I suffer from Amdahl's law. So if you look at this graph, I mean, here we have the number of processors, here we have the speed up, and then we have different lines for different algorithms that, let's say, solve a problem. And these algorithms have different portions of sequential code and code that is parallelizable. And you see that, let's take this line here. I even can't read it myself. It's 90% or so. So this line here is the line of code where 90% of the code is parallelizable. But only, I mean, these 90% are parallelizable. And now if the ideal thing would be you throw double the amount of computing power at the problem, and the time to solution should halve. That would be the ideal case. But for this particular problem, where you can only optimize the 90%, you can throw double the amount of computation power at the problem, but only the 90% halves, and halves again if you double the computation power. And you somehow limit to the sequential part. And what you see here is that already with, let's say, 250 nodes, you hit somehow the maximum you can gain from parallelization. And even for an algorithm that is 95%, that's the green line, parallelizable, you hit this limit around 1,000 nodes. So it's not the case that you can just parallelize every problem and everything is fine in the end. One has to be aware of it. But still, I mean, 1,000 or 500 nodes is already pretty much compared to a single computer, a single node. Okay, so practical limitations. When you use more computers, so you go from one computer to many computers, you have the problem that they have to talk to each other. So you increase somehow the distance between all the transistors that are there. And information can only travel with the speed of light, maximum. So you increase somehow the latency of work that is going on. And this is the first problem. So what you want to do is you want to connect the computers as closely as possible. And in an ideal scenario, you would just take your 100 computers and you would take each 2 of them and put a network cable in between of them. And then everyone could talk to everyone with the highest possible bandwidth, because you buy the best cables, let's say, and with the lowest possible limitations, because nothing is in between them. But this is a problem, because to connect n computers, you need n over 2 connections. So say you have 1,000 nodes. 1,000 over 2 is roughly its order of n squared, so it's a million divided by 2, it's 500,000. So you would need 500,000 cables, roughly, to connect them. This is not possible, right? I mean, I put 500,000 cables in this room, and the room is full. So it's, from a practical point, not possible. It's also quite expensive, I would say. And what people came up with is to change the topology. So to reduce the number of cables, but still with the goal to maintain low latency and high bandwidth. And there are a lot of topologies, actually. Just as an example, here are a few. And they're all trade-offs between cost on the one hand and low latency and high bandwidth on the other hand. So, for example, in a tree, if these 2 guys want to talk to each other, they have to hop over other nodes, and this increases the latency. Also, if these 2 guys and these 2 guys want to talk to each other, they use the same network, so they have to share their bandwidth. So that is where the where the compromise comes in. So the number of connections in a tree is linear with the number of nodes. So if you n nodes, you have roughly n. You need roughly n connections. So the nice thing here at CSCS, we have a very interesting topology which is not on here because it's a bit difficult to draw, which is called the dragonfly topology. And this comes very close to this full connection, to this click. And it works, it's essentially, you can think of it as a hierarchy of clicks. So if you have only a small amount of nodes, it's doable to connect them all to all. And then what in a dragonfly topology happens is you cluster a few nodes, you connect them all to all, and then these clusters you connect by a click again. You will get the slides and the notebook behind the slides, so you can click the link, and there's a very big article about the dragonfly network, which is topology, which is quite interesting, and then have a closer look at it. Good. Now the question, so it's clear we need to parallelize. The question is, how do we parallelize? And there are many ways how to parallelize. Since we are at a HPC center, I want to have a look on the way HPC people would parallelize code, that is using MPI. And because it's a Spark workshop, we also look at how Spark is parallelizing. Or at least I want to do a high-level comparison of the two. Do I have a laser pointer? Good. Okay, so MPI is essentially the de facto standard for high-performance computing. It abstracts somehow away the hardware infrastructure, so it works on Ethernet, on InfiniBand, and you can send messages from every node to every other node. And there are several ways. You can say, I want to send from one node to one other node. I want to send from one node to all the other nodes, and it's very flexible in doing that. And the standard use case for MPI is essentially simulations, weather prediction, molecular dynamics, and so on. And it's quite ripe software, and it is very fast and has a super low latency. So it's really the thing to do on our systems. And there's a lot of support for it. But on the other hand, I mean, it's pretty, it's hard to master. It's not so simple to write code for it. Also, if you do something wrong with communication synchronization, you might even get an overhead. There are deadlocks possible, so you really have to think about the way how to parallelize stuff. Also, if you run code on a lot of nodes and the node dies, you have to manage it as a programmer. So very flexible, very fast, but kind of difficult to master. Then, on the other hand, you have Spark, which is even on a higher level. It does not only abstract away the hardware, the network hardware below, but it abstracts even, I would say, it even abstracts the network away somehow. So there's no real way to say I want to address a single node in the system, or I want that node A send something to node B. Also, communication is not, it's all implicit. It's not that you say, okay, now I want to send something. You do an action, and then the system automatically does the communication for you. And the standard use case is data analytics. It's used in industry, at least in different flavors for creating search indexes, for machine learning, regression, and so on. The benefits are clear. It's quite simple to write parallel programs. There are already many algorithms provided by Spark for machine learning, for graph algorithms, and so on. And since the whole communication part is handled by the system, you do not have to think about also fault tolerance and so on. On the other hand, it's not as fast as MPI. And it might be difficult if you have a difficult algorithm to express it in a MapReduce fashion. That's let's say, the language of the framework. And even if you do so and manage so, it might not be optimal, and then you suffer from bad performance. Good. So now, I hope I made a bit clear that parallelism is good, and we will use we will have a look at Spark in this workshop. And I now want to talk about the mode of operation. So how do we handle, how do we work in our seminar here? So now or later, you will be there will be handouts for Jupyter notebooks. I'm not sure if you're aware of what this is. You will learn what this is. It's essentially a website where you have a piece of way of cells, and each cell can be either text or code, and you can execute the code. And the code then can run on your system or on a supercomputer or wherever. So it's a quite flexible and interactive piece of software, and we will use it here to do the workshop. And there are several notebooks. Every notebook has a kind of a learning goal and sections with learning goals. And the idea is that in the beginning we discuss the goals and the ideas behind the notebook, and then it's your turn, and you will read the notebook. So you will read through it. You try to understand what is going on, and you will do some exercises that are in the notebooks. And we are running around and answering questions and helping you. And if there are problems, then we can discuss it all together. And that will be the general mode of operation. In order to do so, we have to get these notebooks running on your system. Therefore, yesterday, no, that's not true. Last week, I sent around a mail that you please install a VirtualBox, this software that runs virtual machines on your system. So because we are running the notebooks in two phases. So the first one is on your notebook. So you will get a virtual machine which mimics somehow a cluster, a Spark cluster, and you will connect to it. And from there, we do the first exercises, let's say, and later on, maybe another one. The nice thing is you can take this virtual machine image home. You can apply your problem you have in your research field, and you can try to solve it. And if you do not like it, you just delete the virtual machine, and everything's good. And then later this day in the afternoon, we will try to also get you on the supercomputer and do some of the notebooks there. Okay, so then now is essentially time to do two things. First, get the virtual machine image, install it on your system, and second, that's this part. And second is to run the Jupyter notebooks on the virtual machine. Okay, and how does this work? So I prepared a mail. I sent this mail now out to you, and there's essentially this link, the Spark Sandbox, and if you click, you download the virtual machine image, and you can. So the mail is not out yet. You can download the image, and you can import it into the virtual machine, and then you start the virtual machine. The login information is all in. This is all in the email. And then you essentially start the virtual machine and try to run Jupyter Notebook, and you try to connect to the notebook. Yeah, I think that's it. So you can try, and I mean, Maxime and me, we will run around and have a look that everything works. So, but now let's send the mail, and then we can start.